Hi everyone. Today I'll be going over the use of masked autoencoders or MAE to address the challenge of filling gaps in high-resolution sea surface temperature fields caused by cloud cover. My name is Yepremyan, and my co-authors are Edwin Go, Jimbo Wang, and Brian Wilson. There is a need and desire to have high-resolution SST products. It's important in order to understand and predict global and regional climates, as well as to detect small-scale SST fronts that play a crucial role in the exchange of heat, carbon, and nutrients between the ocean surface and deeper layers. However, full-res radiometers cannot penetrate through clouds. Since detection of ocean fronts are mostly based on satellite sea surface temperature and/or the ocean color, it is necessary to find a solution that accurately reconstructs the data below these cloud occlusions. Current methodologies to fill the gap include fusing data between multiple optical satellites, optical interpolation algorithms, and using data from different points of time. The culmination of these methods is the mirror SST product that's on the right. Even with that product, when you go to finer grain detail, there's a lot of aliasing and smoothing that happens. One algorithm that we looked at to solve this issue is the masked autoencoder. Masked autoencoders is a technique developed by Facebook AI Research, which was originally inspired by the training method used for the transformer-based language model GPT. You may be familiar with one of its commercialized downstream products, ChatGPT. Typical vision transformers require a large amount of labeled images, a problem which is actually addressed by language models through self-supervised pre-training on unlabeled data. GPT is trained by taking a sentence, removing some words from the sentence, and then asking the model to fill in the blanks. To transfer this concept to the vision domain, Facebook, instead of taking out words, we remove pixels or patches and train the model to reconstruct the image. The autoencoder system contains two modules, the encoder and the decoder. The encoder model of the image compresses that image into a dense vector, and the decoder predicts the reconstruction. Facebook was mostly interested in the encoder component, which extracts the meaning of the unlabeled sentence or image for other downstream tasks. But for our purposes, we're interested in leveraging that side effect, which is the reconstruction capabilities of the decoder in order to reconstruct SST under cloud cover. We modified MAE to take in SST tiles, and we masked out random patches of that SST tile, and these are the grayed out squares in the image, and feed it through an autoencoder. This is the encoder, which generates a dense vector, and then the decoder, which reconstructs the original image. To train it, we generated a dataset of 1 million synthetic SST tiles. We're using synthetic data for our preliminary exploration so that we can ensure that we have clean data with no clouds. For this, we used ECHO 4320 high-res ocean simulation and did further evaluation and analysis on an additional unseen test set from the LLC 2160 simulation. And then we split the entire ocean into tiles that are 500 by 500 kilometers or 256 by 256 pixels. And we also removed the undersea ice tiles as well as land to simplify the problem, and we can always add those back in later. This results in about 1 million tiles, where we split about 750,000 to training and 250,000 into an unseen validation set in order to test the general capabilities. We trained over 300 iterations and performed random augmentations every time the tile was going into the model. We cropped some of the original 500 by 500 kilometer tile with a random size so that it sees a different resolution every time. We also did horizontal flipping to augment the data set and have more data. The loss function was a simple mean squared error between the reconstructed pixels and the pixels that we actually removed. For our evaluation metrics, we primarily use the root mean squared error because we can measure that in Celsius and it gives us a better measurement of the temperature. We also looked at the spatial correlation and spatial coherence to look into more detail what's going on at the spatial scale. Again, we're mostly interested in the small scale since existing algorithms already work well for the large scales. And how MAE performs when we mask out more and more of the image. So when we train MAE, we vary what is called the masking ratio, which essentially is the percentage of pixels that we mask out. So as you can see, with a masking ratio of 90%, 90% of the image is masked out, or 90% of the pixels are masked out, and we can reconstruct from there. The top is the easier problem at 10% masking ratio, and the bottom is going to be a more difficult problem. One of the first results that we saw when we did this experiment was U shape. So for any given model, regardless of what the masking ratio we trained on, we tested it across different masking ratios, or similar to like cloud fractions. There was this U-shape, meaning that the model only worked well on the cloud fraction or the masking ratio that it was trained on. We otherwise would have expected that with less of the image removed, the problem would have been easier and the model would have done better. So we were expecting a more linear shape. And so that got us thinking, why is this happening? When we think back to the original Facebook model, they trained on images of cats and dogs and cars, and we're training on SST. So that led us to consider the differences between SST and that data set. And I listed those 3 differences here. One, SST has less variety than natural images. You can say it has more homogeneous. Each tile is more correlated with each other. So 2 images of a dog are going to be a lot different than maybe 2 images of an SST. 2, our SST data set only had 1 channel versus 3 channel from the natural images. So there's a lot less information between the different spectrums. And 3, our training data set is 50% of the number of images compared to the one that Facebook uses. In machine learning, when you have less information, this leads to overfitting. So this is our hypothesis that we are overfitting to the train mask ratio that we trained on. So we need some sort of regularization. So how do we regularize? We regularize by using a smaller model. With Facebook, they have a lot of images, so they can really scale up to a larger model. For our MAE, a tiny model works better for us, and that's seen by this orange curve, which doesn't exhibit the U shape anymore, and it's similar, able to get an RMSE of below 0.3 degrees Celsius across different masking ratios. We further were able to improve on these results by training with a random masking ratio sampled by a uniform distribution with a mean masking ratio of 0.5. In other words, instead of having only a singular masking ratio that we're training on multiple masking ratios throughout the training process. The green line shows the results from that, and it achieved a root mean squared error of under 0.2 degrees Celsius for masking ratios of up to 80%, which is a 40% improvement over our original orange results. In this figure, we're showing an example masked SST tile from an unseen LLC 2160 test set with 80% of the values masked. That's the top left. The ground truth is the middle top, and then the MA reconstructed SST tile is the top right, and the bottom row consists of 3 different interpolation schemes. So as you can see, MAESSTRO preserves the frontal structures without over-smoothing. In contrast, our conventional interpolation approaches smooth out the primary front in this example and fail to capture the primary sharp front, resulting in smooth and blurry reconstructions with locally generated bullseye features. Using this model, we also tried it on an example VERS SST tile to see if a model trained on simulation data would work well on real data, and it seems to do okay. We tried it across different test time masking ratios, and this tile in particular got below 0.1 degrees Celsius throughout. And as we increase the masking, as you can see in this GIF, the reconstruction stays the same, and it's able to capture the front. Here we show the RMSE and spatial correlation for MAESSTRO, which is the top row, and the cubic interpolation method, which is the bottom row. MAESSTRO reconstruction exhibits smaller RMSEs for both the SST and the SST gradient, along with higher correlations compared to cubic interpolation. In conclusion, we looked at MAE, which was self-supervised learning method developed by Facebook. We adapted that to train on SST. We encountered an issue with overfitting, where the SST data compared to natural images of cats and dogs was too simple and too homogeneous, and so we used a smaller model and used multiple masking ratios during training. And we showed that it works on our global test set, unseen test set, as well as our example VERS SST tile. Thank you.